Let's talk about powers of 10, specifically as a foundation for scientific notation, which is what we will be studying this week. So, a couple things to recall that should be familiar since we've been through our exponents unit. If you have 10 to the third power, that just means you have 10 being multiplied by itself 3 times. And 10 times 10 gives us 100. 100 times 10 gives us 1,000. Some of you may be familiar with kind of a shortcut with 10. If you have an exponent of 3 on 10, you're going to have 3 zeros. So that's kind of a handy thing to remember. We also need to remember what it means to be a negative exponent. So let's start with a division problem. If we have 10 to the second being divided by 10 to the sixth, that represents 10 times 10 in our numerator and 10 times itself 6 times in the denominator. And when we go to simplify, this should be pretty straightforward for you after our exponents unit. We have 10 over 10, which simplifies down to 1. Another 10 over 10, which simplifies down to 1. So in our numerator, we are left with no 10s. We have 1 times 1 because these two sets of 10 over 10 both simplified down to 1, and 1 times 1 is 1. So in our numerator, we have a 1, not a 0. Those 10s did not go away, they just simplified down to 1s. In the denominator, we have 10 times itself 4 times, so we could write our result as 1 over 10 to the fourth. Now, you might remember there is a shortcut. If we have 2 10s in our numerator and 6 10s in our denominator, you might recognize that these 2 10s are going to cancel out 2 of these 10s, leaving us with 4 in the denominator. But we could also use subtraction and subtract the exponents, which is our shortcut for division with exponents. You subtract them if the bases are the same. So we end up with 2 minus 6, which is 10 to the negative 4. And the reason why it's a negative 4 is because that shows that there were more in the denominator. When we do the subtraction, we get a negative exponent. Or you could represent it with a fraction, showing that those 4 10s are in the denominator. So just remember that powers of 10, if you have a 3 as your exponent, you can think of it as adding 3 zeros. For now, we're going to talk about that more as we get into scientific notation, but at the most basic, without anything else going on, you can add 3 zeros. And then also with division, when you subtract and you end up with a negative exponent, that just represents that there are numbers in the denominator and it's a fraction. Okay, so now that we have those reminders in place, let's go ahead and explore a little bit more with powers of 10, just so that we can be a little bit more comfortable with them and ready to go for our scientific notation. So, for example 1, we're going to have a couple parts to it. Part A, let's just write down some multiplication problems that you probably could do pretty easily. As I mentioned just a moment ago, some of you have that shortcut for multiplying with 10. 2 times 10, 20. You just take your number and add a 0. 7 times 10, 70. 31 times 10, 31 with a 0 put on the end gives you 310. So for all of these, that power that we're too lazy to write on here is a 1. And essentially, with these particular problems, we did end up adding 1 0 because we have a power of 1 on our 10s. Now, you kind of want to be careful about that idea of thinking of it as adding zeros, because as we get into scientific notation, you'll see that other things can occur. But for now, like I said earlier, the most fundamental thing with these particular problems, you are just adding a 0. Part B. If we have 9 times 10 to the 5th, if we follow that pattern, we can write our number down and we can put 5 zeros behind it and get our answer, 900,000. Maybe we have 21 times 10 to the 7th. We write a 21 and then we put 7 zeros behind it. So here's kind of a little preview of where that becomes a little bit trickier. Let's say we have a number now that has a decimal in it, and we're multiplying it by a power of 10. We don't just write 5.3 and put 4 zeros after the 3. That's not what's happening here. So let's go back to this one and talk about another way to look at it besides just by adding zeros. We'll end up with the same answer, but it helps us find the answer to this one. So if we think of this instead as a 9 with a decimal, every time you multiply by a power of 10, you're moving the decimal one place. And I guess it might be more helpful to go back up here. If we have a 2 and we multiply by 10, we move the decimal one place, fill in that empty spot with a 0, and we get 20. We know that 2 times 10 is 20. That's just the mechanics of it that will help us as we get into more complex problems. So again, if you think of 7 as a 7 with a decimal after it that we're too lazy to write, we multiply by a power of 10. We've moved the decimal over one place, fill in the empty spot with a 0, and we end up with 70, which we already knew. Same thing happens here. 31 with a decimal after it. We're just too lazy to write that decimal. When we multiply by 10, that decimal's moving over one place, fill in the empty spot with a 0, and again, we get the 310 that we already knew it would be. So with that idea in mind, now we can take this 9 that has a decimal there, we're just too lazy to write it, and instead of adding 5 zeros after the 9, let's think of it as moving the decimal 5 places. Up here, we move the decimal 1 place every time. Now let's move it 5 places. So we can move it 1, 2, 3, 4, 5 places and fill in all those empty spots with zeros. And you can see that we have added 5 zeros. So we get the same result. It's just an alternate route to help us with problems like this one. Let's look at this one real quick, and then let's talk about this one. So here we have 21 being multiplied by 10 to the 7th. And instead of just adding 7 zeros, let's go ahead and write down the 21 with the decimal where it would be if we wrote the decimal. We're just not going to because we don't have to here, but it's helpful here. So let's move it 7 times. And each time you move it, you need to fill those spots with zeros. And we've added 7 zeros, and now the decimal's sitting at the end, which is exactly what happened here. Just like we moved the decimal 5 places here, and now the decimal's sitting here, and on up if you wanted to keep going. All right, so now how does that help us with this one? Well, what that does for us with this one is it sets up a method to find the answer. If the decimal is sitting right here, and we need to move it 4 times, now we're only writing 3 zeros. And the answer is 53,000. So what happened here is this is not the number of zeros that we add to the number. Here it ended up being the number of zeros that we added to the number. Here it ended up being the number of zeros we added to the number, and same up here. But that's only because the original number had a decimal sitting at the end, and there were no numbers to jump over. Here, the decimal is not at the end, and we need to jump over the 3 as we're multiplying by 10 to the fourth. And that ends up giving us only 3 zeros in our answer. So you might want to begin to change your thinking from that's the number of zeros you'll see in your answer to that's the number of places you move the decimal. And that will help you tremendously as we study scientific notation. All right, so now let's talk about those negative exponents. In the beginning, we talked about 10 to the negative 4 and how it really represents that we have 4 tens in the denominator being multiplied together and 1 over 10 to the fourth. If you wanted to write it out the long way, you could write it out like that. But at this point, you know that 10 times 10 times 10 times 10 is going to give you 10,000. 1/10,000. Now, 1/10,000th as a decimal, because decimals are what we use when we talk about scientific notation, you need to remember your place values. So the first place value after the decimal is your ones. Sorry, not your ones, your tenths, then your hundredths, then your thousandths, then your 10,000ths. So tenths, hundredths, thousandths, 10,000ths. That's our denominator, 10,000th. So that's the last place value that we are going to be using. How many 10,000ths do we have? 1. So that's what sits in the 10,000ths place. And you fill in those empty spots with zeros. And so our answer is 0.0001. Here's another example of how the power does not tell you how many zeros there are. The power tells you how many places you're moving past the decimal. In this case, we're moving past the decimal to create a very small number, which 1/10,000th definitely is. In our previous problems, we were moving the decimals to create large numbers, and we'll talk more about that in a second. Let's go ahead and look at an example, again with the negative exponent, just to kind of put another perspective to it. If we have 7 times 10 to the negative 4, and oftentimes they won't use a dot. I've seen both, but more often with scientific notation, they use the X to show multiplication. So just kind of be prepared for both. This is like saying we're going to take 7 and multiply it with 1 over 10 to the fourth, which we already know. That's going to be 7 times 1/10,000th, which gives us 7/10,000ths. So it's very similar to this right here, except now our numerator is a 7 instead of a 1. So we're still going out to the 10,000ths place, so tenths, hundredths, thousandths, 10,000ths. But now we have 7 of those 10,000ths. So the 7 sits in the 10,000ths place. Fill in the empty spots with zeros. And this is how we write 7/10,000ths. All right, so let's do a quick comparison just to sum up and finish laying that groundwork for scientific notation. We are comparing 10 to the 5th power with 10 to the negative 5th power. This creates a very large number, 100,000. This creates a very small number, 1/100,000. The key to recognizing the difference in this form is if you have a positive exponent, you will have a large number. If you have a negative exponent, you will have a small number. So that's kind of your hint with scientific notation. Look at the exponent. If it's positive, you are creating a large number. If it's negative, you are creating a small number. We'll talk more about that in our next lesson.